Unit 7, Day 4. Start on page 12 of your packet. And we've been talking a lot about slope fields, and we know that slope fields are just basically derivatives. So what we're going to do is we're going to find the general solution of those slope fields or those differential equations. And we focus on first order differential equations. First order differential equations are differential equations that just have the first derivative, not the second derivative. That's a whole different course. So we just focus on the first order differential equations. So our question is, what is a general solution? Okay, so we know that a differential equation is an equation involving derivatives. So if it's a first order differential equation, then it's an equation that has the first derivative in it. So like dy dx equals something in terms of x and y. That general solution then, I guess we'll get to that in a second. The definition then of a separable differential equation, remember differential equation I refer to as DE, is this. So it says a first order differential equation y prime equals some function of x and y is separable if this occurs. So in other words, this is separable if I have dy dx equals and then something in terms of x times something in terms of y. So I have to have a product here in order to separate them. And then the reason I need a product here is because then I can divide by h of y and multiply by dx, and then my y's are on one side and my x's are on the other side, and that's what it means to separate the variables. That being the case, though, we end up with, a lot of times we end up with h of y in the denominator, so we have to put on this criteria here that we can't have h of y be 0 because we can't divide by 0. Just a caveat here, sometimes we don't have a product, sometimes we have a quotient. So we have like g of x divided by h of y, in which case then it would be a multiply and multiply sort of mathematical operation. But if you remember that a quotient really is just a product of the numerator times 1 over the denominator. So we could always rewrite that as a product. So when I say it's a multiply divide thing, meaning when we move h of y, we're either going to multiply or divide. And I'll get into the specifics as we go through the examples. Okay, so because this is a separable differential equation, because this is in general a differential equation, if we can separate out the variables, we can solve it. And the way we solve it is we do the antiderivative of both sides. So in very specific terms, the general solution is just the antiderivative of the differential equation. And this general solution represents a family of functions. And we'll get into more about what that means as we go through examples as well. So the steps for separating, the nice thing is write them down, follow them, you won't go wrong. They apply for separating any first order differential equation that's separable. So the first thing we're going to do, like I mentioned a little earlier, is we're going to separate variables by either multiplying or dividing. We're going to look at all the y, all the things involving y on one side, all the things involving x on the other. So for instance, if we started with this, like I mentioned a little earlier, we would divide by h of y, we would multiply by dx. It would look like this, right? Dividing each side by h of y moves h of y into the denominator here. Multiplying by each side by dx moves dx into the numerator here. Now I've got all my y stuff on the left, all my x stuff on the right. I can do antiderivative of both sides. So that's what I mean by multiply / divide process. So that's exactly what step 2 then is. We're going to take the antiderivative of both sides. So we're going to do our derivative rules that we've been working with for now 2 minutes. And then lastly, we're going to solve for y because they want a solution, and we write solutions in terms of y equals. So this involves a little bit of algebra, maybe some logarithmic or trigonometric stuff. Depends on the differential equation that we're solving. Okay, so let's look at an example here. So before we look at this, well, let's look at this here. Let's look at the question. It says, what is the general solution to the differential equation dy dx equals root y minus root y sine x for positive values of y? So in other words, obviously we're not We don't deal with the complex world here in calculus. We can't have negative values of y and have complex solutions. We need to make sure that we restrict the domain. Well, it's kind of the domain, it's really the range, but because it's a y, but we have to restrict it to positive values. Before we go into that solution, let me just look at this form here. Root y minus root y sine x. I'm starting out with kind of a tricky example. Going back to this definition here, that our differential equations are separable if we have a product, and that product is going to be an x factor times a y factor. If you notice in this example, we don't have a product, but we can get a product if we factor out the square root of y. So that's what we're going to do. We're going to factor out the square root of y from each one of these terms, and then we can write this as y times 1 minus sine x. Now I have a product. I've got something times something, and I've got a term, a factor of my product, so to speak, because factors are the pieces of the product. A factor that has all the y stuff in it, and a factor that has the x stuff in it, and my constants is no big deal because we didn't take the constant. So now I'm ready to go through those steps. So in this case, I'm going to divide by root y, and I'm going to multiply by dx. So dividing by, if you can kind of envision this, divide by root y, do that to both sides, 1 over root y, right? Multiply by dx, so times dx times dx. Okay, so there's my times dx. Those cancel. I get this. Now I'm going to divide by the root y. And so I end up with an expression that looks like this, right? And notice I slid over, instead of just saying dy divided by root y, I said 1 over y times dy. It doesn't matter. You could keep it as dy over root y, but we want to recognize that this, when we do antiderivative, we're just going to write this as negative half power through the reversal of the power. So now I have my variables separated. I've got my y's on the left, I've got my x's on the right. I'm going to go ahead and write this with its negative power. And now I can go ahead and do the antiderivative of both sides. So let's do the y side first. So bump up the power by 1, that's positive half, divide by the new power. So this is going to be y to the half divided by half. Then on the right side, antiderivative of 1 is x. Antiderivative of minus sign is minus a negative cosine. Right? So be careful about your signs there when you look at the sine and cosine. Now, we've done an antiderivative of both sides. I haven't mentioned the plus c yet, right? We see it in the answer. Where does the plus c go? We know that constant of integration is just a number. So we don't put it on both sides. We put it on the x side only. And the reason being is because it makes math simpler. But in reality, if we would put a plus c over here and a plus c over here, and those were just numbers anyway, we could move the 1 on the y side over to the x side and just have 2 numbers that I need to subtract. So instead of complicating the math, because we got to solve for y anyway, we leave it off the y side. And we just say, well, let's just put 1 on the x side, and that c represents the difference of the 2 constants. So we just slap it on the x side. We don't really think too much about it. It's just a number. All right, so we've done really all the calculus. So the question is, can we pick out the right answer at this point? So give that a little bit of thought. Now, the one thing I'm focusing on right now is that I have a y to the half power right here. That's a square root of y. If I have to solve for y, that means I have to square something. So at this point, I'm going to, since I'm dividing by a half, I'm going to multiply by a half, multiply each side by a half, just so you can kind of see this better. If I have to square this, then I've got to either end up with c or d. Okay, and so at this point, you can kind of speculate that when I square this, I'm going to have to square the whole thing, which means I have to square the whole right side, which means this becomes a fourth, and then I just stick a power of 2, make sure I got everything in the brackets, including the c, make sure I have a power of 2 at the end there, then I've solved for y, it's definitely d. So when you look at these two answers, I thought maybe I had both of these highlighted. I guess I didn't. But this we left the c out of the squaring here, and we can't do that. We definitely square the right side, so we definitely have to square the left side. Excuse me, I said that backwards. We definitely square the left side, so we have to definitely square the right side, and we have to square the whole thing. So that's why D is the appropriate answer here. Okay, let's take a look at example 2. Finding the general solution directly. This is a flat out antiderivative. So why don't you stop the video and try this on your own? Notice there's no y here. So it's a plain old antiderivative. That's what I call this. So if you stop the video, all you're going to do is multiply by dx and then do an antiderivative. Go ahead and try that on your own. Okay, so if you're tuning back in, I'm assuming you've tried this on your own. So we have this as, we call it differential equation. It's really just, I mean, whenever we say differential equation, it's just a derivative, right? And so we can approach this the way we approached antiderivatives in the last unit, right? If my derivative is secant squared, what function did I start with? So we can ask that question, and we probably could pick up the correct answer already. But let's go ahead and separate the variables. So multiply by dx, those cancel on the left. I have this. Notice there is no y here in this expression of the differential equation. So that being the case, we don't have any y to move. We don't have any y to divide or multiply to get onto the dy side. So we're done. We're just going to do the antiderivative of both sides here. Remember, antiderivative of dy, there's a coefficient here, it's 1. So this is really 1 dy. And just like on the last screen, where we're integrating 1 by x, we're going to integrate 1 by y on the left side here. So y equals, and then if you remember your trig derivative rules and run those backwards, we know this is tan x plus c. So the answer's got to be A here. Okay, going on to example 3. So example 3 is finding the general solution directly with the use of. So this is a little more complicated just because of the antiderivative process. So here's our differential equation, dy dx equals x cosine x squared divided by 4y for y's are greater than 0. So looking at this, do you see the use of that we're going to have to do the antiderivative on the x side? Okay, so kind of keep an eye on that. All right, so here's our differential equation. So we're going to multiply by dx, and that's going to move the dx to the right. We're going to, now this is one, remember when I said step 1 is a multiply slash or divide sort of process. Depends upon what we have to do to move the y. So notice that in this scenario, the y is in the denominator. So this is a multiply. We multiply by dx, and then we're going to multiply by y here. Now, interestingly enough, notice I'm just taking the y. I'm leaving the 4 on the x side. You can take the 4 with you if you want to. But the thing is we always have to solve for y. So I'm not going to take the 4 to the left just to take it back over to the right. So I'm going to leave the 4, just move the y. Multiplying by y cancels it off the right side. So I have y dy equals 1/4 times x cosine x squared, or x cosine x squared over 4 dx. Okay, now I can do the antiderivative of both sides. So I'm going to flip over to the next screen here. So that's what I had on the previous screen. So looking at this, okay, if we can kind of do a little prediction here. I see that I'm taking the antiderivative of y dy. We know we're going to get ay squared over 2 when we do the antiderivative. And if I have to solve for y, that means I got to end up square rooting something eventually. So we already can kind of narrow it down to either A or B. Okay, so this is kind of like in the last unit when we were working with the inverse trig antiderivatives. Remember, I was I kept saying, sometimes you don't need to read the whole problem to figure out what the answer is. You just need to see the pattern. And this kind of holds true too on these multiple choice questions. Sometimes you don't have to do the whole process. Save that time for when you have a free response question. Sometimes you can start picking out the answer before you get all the way done. So that's what I'm doing here. Okay, so I'm going to go ahead and do an antiderivative here. Y squared over 2. Save the plus c for the x side. And then this one, I'm going to factor out the 1/4. So I have x cosine x squared dx. So do you see the u sub here? Right? I have function and the derivative, single trig. So the tip was if it's a single trig function, then the u is what's in the brackets. Remember that tip? The other tip, just a caveat, but the other tip was if there's multiple trig functions, then the whole trig function is the u sub, right? And we don't have that here because we don't have multiple trig functions. So we are going to set u equal to x squared. We're going to differentiate this. Du dx is 2x. We're going to do our old switcheroo here so that we have dx is du over 2x. Remember, the x's are going to cancel. This is supposed to be here. This is supposed to stay for a reason. Okay, so substituting that in then gives us this. And our x's, we can see that our x's are going to cancel. So I'm also going to factor out the half because we have a 2 in the denominator. So x cosine u du over x, we can move those x's, and I have that. All right, so I'm going to integrate my cosine, give it a sign, put my plus c over here. So can you just kind of pause the video and look at options A and B, and can you determine what the answer is without even going any further? All right, so if you paused it and you're coming back, hopefully you've concluded that, well, since I have a half here, I got to multiply by 2. This is going to end up being a 1/4, so it's got to be b. And then I'm going to have to end up square rooting. And I'm going to put the x squared back where the u is. Okay, so dot, dot, dot. You know it's definitely b. Okay, I'm not even going to finish that up there because it's really, on a multiple choice question, it's really not worth my time to do that. Okay, so I'm being a little facetious here. Here are some seemingly random questions, okay, but they are good uses or good applications for differential equations. That's what I'm going to ask you. Hey, it's the equation of the tangent line problem again, right? I've asked you this on every test, almost. I think actually pretty much every test. So it's coming up again. We love to hit this question in so many different ways. But this is one way we can hit it and tie it into the differential equation unit. And that's really important because College Board only has 6 free response questions they're going to ask you. So they really got to combine units on those questions. And this is one way to do it. So we have y equals f of x, and it has this differential equation. Right? We don't know what f of x is. We could separate this and integrate this out. But that's not what the question's asking. But it's a first order, so we could do that. Okay, so let's write the equation of the tangent line for the function f, where f of 2 is equal to -1. So what information do we have here? Well, we've got this. That tells us my x and my y. Right? It tells me my x1 is 2, and my y1 is -1. Now I need my slope. Well, when I say slope, you think derivative. Here's my derivative. So my slope is my derivative evaluated from x is equal to 2 and y is equal to -1. So we are just doing a straight substitution here. I'm going to stick in 2 for x. See, x is 2 squared instead of x squared. Y is -1. Okay, math it out. We got 1 minus 2 over 4. That's 1/2. So we got a half. This is -2. So a half times -2 is -1. So my slope must be -1. So now I've got the pieces. I've got my point. I've got my slope. I'm going to grab that point slope one. Okay, I'm going to plop in my x1, my y1, my slope, and I'm going to be done. So my slope is -1. My x1 is 2. My y1 is -1. So this changes the sign. And there's my tangent line. Okay, so let's take a look at this other random question. 5, we're going to bring back concavity from unit 5. Yeah, I think it's right. Yeah, unit 5. Concavity we know is related to the second derivative. So the first part of this question is saying find the second derivative in terms of x and y. here's the first derivative. And then from that result, we can determine concavity for all solutions in quadrant 3. So we have to know something about quadrant 3. That's the lower left-hand part of your coordinate plane. Okay, so we'll start with the first derivative. It's x squared over y. I have to differentiate this. It requires the product or the quotient rule, excuse me. So that we're going back to our implicit base, right? Because we have a derivative in terms of x and y. I have to differentiate this. Not only am I getting a quotient that I can do quotient rule for, but I have a y in this here, so I have to do this implicitly. So remember, our quotient rule is low d high minus high d low over low squared. So the second derivative then is low. That's the denominator, y. Low d high, derivative of the numerator is 2x minus high x squared d low. This is the tricky part. Derivative of y is 1y prime. And then over low squared, y squared. Okay, so my second derivative has a first derivative in it. So I'm going to need to, I need to get rid of this y prime because I have to have a second derivative in terms of just x and just y. So we're going to take x squared over y and stick that into the y prime. So it's going to look like that. I also don't need to write that coefficient differently. Okay, so I'm going to simplify this part of that quotient rule, and that's going to be x to the fourth over y. Now we can talk about what happens in quadrant 3. So we know in quadrant 3, that's the lower left-hand part of our coordinate plane. Our x's are negative and our y's are negative. So that being the case, then we can start determining each one of these terms, whether they're positive or negative. So let's take this first one, 2xy. Okay, so 2xy, since x is negative and y is negative, it's 2 times a negative times a negative. It's a positive number. So then we know this whole thing is positive. Now let's look at this next one, x to the fourth over y. Well, x is negative, but to the fourth power it's going to make it positive. And if y is negative, we have a positive over a negative, which is negative. Now let's take a look at the denominator. If y is negative, then and we square it, then y squared ends up being positive. So we have a positive minus a negative over a positive. Okay, so that makes the second derivative in its entirety, that makes it positive. Okay, so we're not done yet because we have to connect the fact that this is positive to what it means to be concave up or concave down. So we know that the second derivative being a positive, since the second derivative is positive, the function is concave up. That's what positive second derivative means. So that is the statement that will give us the 4 points there. And then the supporting evidence is this rationale here. And the fact that we calculated the second derivative correctly here. The stuff in blue is kind of connecting the dots between the second derivative and making this conclusion. All right, so when we get back into the classroom, we'll go over the takeaways and then we'll work on some advanced topic questions using the separation of variables to find our general differential equation. Actually, before we do that, I want to talk a little bit about that general form of when we solve differential equations. So that plus c on the end puts it into like a family of functions. Okay, and we'll get more into what that means as we talk about, remember I said that there was a particular solution to it. So we'll talk about a little bit more of that, but that random constant of integration means I can put any number there and basically offset the function vertically or vertically upward or vertically downward, but I don't change the function's shape. I'm just shifting it. So I'm not changing any aspects about the derivative of that. That's why the antiderivative of that family of functions.